Good morning. We started looking at multipole expansion, and I want to show you why all the math we did to come up with this multipole expansion in lecture 11 is useful. So to do that, let's take a step back and think about moving a charge from our point A to point B. So let's say I have point A to point B, and I'd like to move a charge Q from A to B. And I want to do that in the presence of some electric field. So you can imagine, some charges sitting here and producing an electric field, right? So the electric field here is denoted by E. And so I would like to see how much work is done to go from B to A to B in this electric field E produced by this charge distribution here. So to do that, we want to take this from A to B with a force that exactly opposes the force from electric field. So the force from the electric field is QE. So to take this particle from A to B, we need to apply a force, right, to oppose this QE. So then if I see the work done is simply going from A to B, F dot dr or dl. So then here this would be, this is F applied, because we're looking at the work done by the applied force to take charge Q from A to B. So the applied force is negative to the force that is acting, so that is negative F dot dl, or negative Q times E dl, right? If we are assuming the simple case of E along dl, so that will give us minus Q, right, A to B E dl. And if you look at this negative sign and combine it with this essentially gives you the potential. Recall that potential, negative gradient of potential, is electric field. We looked at the negative sign when we were trying to define the potential in some lectures back, and that negative sign appears because we're looking at how much work is done by the applied force in taking the charge from A to B. We're not looking at the work done by the electric field. When we look at the work done by electric field, you would not have this negative sign. So that's where the negative sign comes from, because we're applying a force opposite to the force because of the electric field to carry the charge from A to B. So then essentially you can write the work done as the charge times phi, the potential, right? So so if you look at, for example, how much work is done to assemble a charge distribution, if you have the first charge, there are no charges present in the planar, so you can bring your first charge, Q1, from infinity and place it here. So this comes free because there was no potential to begin with. Remember that work done is Q times the potential. So now if I bring charge Q2, right? If I bring charge Q2 now, charge Q2 will feel the potential of Q1. So the work done in bringing the second charge would be Q times phi from the first charge, which is KQ1 by R, where R is the distance between charge 1 and charge 2. So that would be the work done for Q2. So suppose you brought Q2 here and put Q2 here. This is R12. Now, if you want to bring another charge Q3, then this Q3 will feel the effect of both Q1 and Q2. So work done to bring that charge would be, this would be Q2, would be Q3 times the potential from the first one, KQ1 by R13, plus KQ2 by R23. So the third charge, when you bring the third charge in, it is feeling the potential from the first one and the second one. So if you do the similar analysis for the work done for the fourth charge, right? If you place the third charge here, Q3, this one would be R13, this would be R23. So now if you were to bring in the fourth charge, it would feel a combined effect of all the three charges. So you have Q4 times potential due to the first one plus potential due to the second one plus potential due to the third one. So now if you were to look at the total work done in assembling these four charges, then you will have to add up all these terms. So the total work done would be Q2 K Q1 Q2 by R12, that is this term, plus K Q1 Q3 by R13 plus K Q1 Q4 by R14 plus K Q2 Q3 by R23 plus K Q2 Q4 by R24 plus K Q3 Q4 by R34. Right. So now, in fact, by looking at this trend, for the first charge, there is no work. For the second charge, you have one term. For the third charge, you have two terms. For the fourth charge, you have three terms. So for nth charge, you will have potential from n minus 1 charges that you brought before them. So work done for the nth charge would be simply whatever is the charge Qn, right, times the potential from Kq I divided by Rin. So this Qi and this is summed over I is equal to 1 to n minus 1. So for the first charge you would have Q1 by R1n. For the second charge you would have similarly KQ2 by R2n, so on and so forth. So that would be the nth term. So based on this, you can write total work done then as simply K times. K is constant all throughout, so you can pull it out. We are summing over Qi Qj, right, and Rij, and here I have a summation on J where J is going from 1 to n for each charge I am bringing in, right? And J is greater than I. So for the first charge, there is no potential, so it is 0. For the second charge onwards, I would start getting terms like Q1, and when J is greater than I, that is Q2, so I'll get a term like Q1, Q2. So if I is equal to 1, I'd get Q1, and J is greater than I, so get Q2. So I would get a term like Q1, Q2 by R12. So an easier way to sum this up is remove this constraint. If you remove that constraint, basically you would be doing you would be double counting. Instead of just Q1, Q2, you would also do Q2, Q1, because now for Q2, Q1, this J is less than I. So you would just end up double counting. So an easier way to do this is just take half of just I is equal to 1 to n, J is equal to 1 to n, Qi, Qj by Rij. Right? Or you can write this as half of sigma I is equal to 1 to n pull Qi out, and then from j is equal to 1 to n, accepting j equal to I, because a charge we're not considering the potential of Q2 itself as it is coming into Q1, right? So when I have a charge Q1, if I'm bringing Q2 in, I'm only looking at whatever is the potential from the charges that are already at this point. So I would not be considering Q2. So if I pick Q2 here, I should not consider Q2 in this, right? So that's why we have J is not equal to I. And here I can write this as KQJ by Rij. Or simply this, I can write it as half sigma I is equal to 1 over n Qi, and this is simply the potential phi of Ri. So this half term comes in because we want to do a little bit of cheating here to make the summation easy. So we added this, we removed this j greater than I effect, and so we double counted like Q1 Q2 and Q2 Q1. So that's where the half comes from, right? So now you can see that if I have any charge distribution in a potential, I can get the work done to assemble it uh, using this, right? And so if this much work is done to assemble the charge distribution, that means the charge distribution has stored whatever work is done here, because it has taken energy to put these charges together. So if you were to, these charges are in this configuration, in the stationary configuration, for example, right? So it has taken some work to bring them here from infinity, right? So whatever work is done is stored as the energy of the charge distribution. So this work done is stored as the energy of the charge distribution. Now you can clearly see here, if I look at this term, sigma I is equal to 1 to n q times qi phi at Ri, then you can clearly see that if I have any kind of charge distribution, I can chop it up into small parts, right? And then I can just take this, convert this into an integral, and make this into rho of r, right? Rho of Ri, phi of Ri, d cube Ri, right? So I'm just treating each cell as a point charge and generalizing this. So the total energy we can write then, or the total work done to assemble the charge would be half rho of r phi of r d cube r. So when you look at something like this, you will be able to understand why multipole expansion becomes very important. So we'll hold on to this and go back and recall what we did with multipole expansion. So in terms of multipole expansion, we were looking at the potential function itself. So we had our potential function phi as a function of r, which was equal to k times integral of rho of r prime d cube r prime divided by r minus r prime. So the way we got this was, if you have, suppose you have a charge distribution like this, and you would want to figure out what is the potential at this point P. This point P is itself at a distance of r, and you can break this up into small tiny cells, and you can index each cell as some r prime, and you're going over each of these cells. So you're spanning over r prime, so you're counting each of these cells within this volume, and that's what this integration gives, right? And r minus r prime is the distance between the point P and any cell that you are in. So this would be r minus r prime, right? So So what we did in multipole expansion was we looked at this function. So we looked at f of r prime as 1 over r minus r prime, and we wanted to set this r prime to origin to 0 and expand this function. And that's what gave us the multipole expansion. So we expanded this function f of r prime as using a Taylor series. So f of r prime set to 0 plus ri prime dou f by dou ri prime, and this set to r prime is equal to 0. A summation is implied plus half ri prime rj prime dou square f by dou ri prime dou rj prime. And this set to r prime is equal to 0 and so forth. And we have taken this function and I actually saw that this becomes just simply 1 over r plus this becomes ri prime ri by r cube plus this becomes half ri prime rj prime 3 times ri rj minus r squared delta ij divided by r to the power 5. So we saw that we derived these things in the last lecture for deriving the multipole moment. And so we got this expansion and we simply tried to plug in this expansion into the equation for potential. So when we do that, we get this phi of r as, I'm just going to write k outside, and square root, integral rho of r prime. The first term is 1 over r, so d cube r prime, plus the second term is rho of r prime ri prime by r cube d cube r prime, plus the third term was half rho of r prime ri prime rj prime 3 ri rj minus r square delta ij divided by r to the power 5 d cube r prime, so on and so forth. So now if I look at this integral term, then you see that the integral is over r prime because you're going over each cell and then looking at how much potential is coming from that cell. So r is independent of that, so you can pull that out. So I can just write it as 1 over r and an integral of rho of r prime d cube r prime. But then you see that this integral should just give you the total charge, right? So we call this the monopole. So this is like the total charge of that volume. Then if I look at this, again, r cube and ri are independent of the integral, right? So I can write this as ri by r cube integral of rho of r prime ri prime d cube r prime. And this is what we called as the dipole moment. So what this is doing is, for example, if you have, let's say, a positive charge and a negative charge around the origin, and you're looking at a point P which is very, very far away. And from this point, it looks like the total charge, because positive and negative are so close and you are so far from these charges that it looks like the total charge is 0 because you have equal positive and negative, right? So it looks like neutral, right? But they're not really canceling each other away because they are at some distance, right? So although this first term may be 0, the second term will not be 0 because you have indeed a dipole here, and the positive and negative charges are not right on top of each other, they're at some distance. So although it is much smaller compared to the distance between origin and the point P, still there is some effect, and that effect is captured by dipole moment. Now, what if you had a charge distribution which had, for example, another dipole that is like this? So I have two dipoles, or let me even give a better way. So instead of having one dipole, let's say I have one dipole of plus minus and another dipole of minus plus. Now, if I look from very far, there's one dipole like this and another dipole like this. So overall dipole moment would also be zero. Yet the effect of this is not zero, although the total charge in the total dipole moment is zero. And so then you will basically get this third moment. That's why it's quadrupole moment. Because here you have two dipoles or four poles. So just by looking at the charge distribution that we are interested in, if you're looking at most of the times, we're looking at, for example, in solid state physics, we will be looking at things like an electron cloud that is slightly displaced from its atomic nuclei. So overall, it is charge neutral because the atomic nuclei have exactly equal and opposite charge to the electron cloud in a neutral atom. Yet there are these dipolar effects which come from the electron cloud being momentarily displaced from where it was. So there, these dipole and quadrupole movements become very important because the total charge is zero, right? And we're talking about very far away. And to get a sense of this, you can think about this. So an atom is around 10 to the power minus 10 meters, let's say, and even if you are at the level of one atom thick sheet, well, it's a few nanometers, right? So then that's roughly if you say 100 nanometers, right, that's roughly 10 to the power minus 7 meters. So you're already at 1,000 times this distance, right? So from these distances, the total charge 1,000 times the distance, you don't see the total charge effects, but you rather see these dipole and quadrupole effects, just like how I explained here. So that's why these movements are important. Now let's look at the quadrupole movement in a little more detail because there is some mathematical manipulation that we will do to make this easier. So the quadrupole movement itself looks like half integral, and of course there is k rho of r prime d cube r prime divided by r to the power 5 ri prime rj prime 3 ri rj minus r square delta ij. So now let's look at this term in the brackets here. What do we mean by 3 ri rj minus r squared delta ij? Recall that this ri rj are the components of the vector. So if I had this vector, I would write it as some r1, r1 plus r2, r2 plus r3, r3. So in general, this ri's are the components r1, r2, r3. Right, and I and j are repeated, so we're going to sum them over, right? So if I sum it over, essentially, if I look at terms where I is not equal to j, then you can see that the second term is essentially 0 when I is not equal to j. So then I can write this as 3 ri rj when I is not equal to j, plus when I is equal to j, I get an extra term of minus r square. So then I would have, for terms where I is equal to j, I would have 3 times ri square minus r square. So if you look at this one, for example, if I were to just do this 3 ri rj minus r squared delta ij for I and j going from 1 to 3, there is x, y, z, then this term would look like, for x it would look like 3x squared minus r squared. For y it would look like 3y squared minus r squared, and for z it would be 3z squared minus r squared. So here you're adding 3x squared plus 3y squared plus 3z squared. So we have 3 times x squared y squared plus z squared minus r squared. And this is nothing but r squared, so minus 3r squared, because you have 3 times. And so 3r squared minus 3r squared essentially gives you 0. So the term that is related to this delta ij essentially leads to a 0 term when I is equal to j. So using this, we can, to symmetrize the primed coordinates with the unprimed coordinates, what we can do is, instead of writing simply ri prime rj prime, we can write it as ri prime rj prime minus 1 over 3 r prime squared delta ij. So this essentially doesn't change anything with the integration, because the extra term we added would anyway end up giving us 0, right? Like we have seen, because the way the summation is, it adds up to 0. So whether I write 3 here or 1 over 3 here, it doesn't matter. But the summation essentially gives us 3 times x squared plus y squared plus z squared minus 3r squared. So it zeroes out. So just to make this symmetric with the unprimed coordinates, we can do that, or I can write this as 1 over 3 3 times ri prime rj prime minus r prime squared delta ij. And so this 1 over 3 can be carried up front, and we can rewrite the quadrupole term as 1 over 6 k times rho of r prime d cube r prime by r to the power 5 3 ri rj minus r squared delta ij 3 ri prime rj prime minus r prime square delta ij. So we're sort of symmetrizing it. So now if you take out all the prime coordinates are this, that gives you the quadrupole moment. And these other coordinates are rij, the integration is on the prime, so these are essentially a constant. So if you go back to the potential and the multipole moment, so the way we defined and did the Taylor expansion and look at those terms, then we see essentially what we have for phi of r is we have 1 over r rho of r prime d cube r prime, which is the total charge, plus ri by r cube r prime rho of r prime d cube r prime. This is the dipole moment, which we are going to call P. And you see that this is for each coordinate I, so I can call it as Pi. Plus, then here I have, from the mathematical trick that we just did, I have 1 over 6, 3 times Ri Rj minus r squared delta Ij by r to the power 5, and the integral would have a term like this again, 3i ri prime rj prime minus r prime squared delta ij times rho of r prime d cube r prime. So this is what we call as the quadrupole moment, qij. So these are very useful to look at different charge distributions, especially, for example, if I want to look at a dipole, like I said, I don't need to consider this term because the total charge is 0. I can directly go to this term. And here, what I see is I have one pi for each coordinate. So I would have here ri by r cubed, and here I get a pi. So I essentially have I summed over. So this is pi times ri, or I can just write it as p as a vector and r as a vector, p dot r, right, by r cubed. So that gives us very straightforward. If I have a dipole here with a dipole moment p, and the dipole moment is defined as this, then if I'm at a distance r from the dipole, then the potential here is just p dot r by r cubed. It's just very straightforward. If you have not followed the multipole expansion, I strongly urge you to go back and redo the calculation with me again. Maybe you need another time, another calculation, and only when you do, it makes more sense. So even if I explain much better, it may not make sense unless you go through this calculation yourself. So I strongly urge you to take a piece of paper and, after having watched this, try to work it out yourself without looking at the video. And then wherever you have questions, you can go back to the video and look at it, so that, take help wherever you get stuck, but try to do it yourself and see, what you get and see if it makes sense. And to see if this makes sense, you have r cubed, but you have here r, and it's sort of still going as, kind of r square behavior. So the electric field would go as 1 over r cubed then. This is only the potential. This is not the electric field, right? And you would have one r cubed term and one r to the power 5 term when you differentiate this, because you have r in the numerator and r cubed in the denominator. So the dipole field doesn't go off as inverse square. It goes off as this, and that can be very easily seen from these multipole moments. Now, we talked about the total work done, or the total energy in assembling a charge distribution, and we have seen that is related to the total work done was half of rho of r, phi of r, d cube r. So now we can look at this, and if I Taylor expand phi of r, right, around r is equal to 0, right? These are all vectors in general. So if I Taylor expand this at r is equal to 0, then I would have this plus ri dou phi by dou ri at r is equal to 0, plus similarly half ri rj dou square phi by dou ri dou rj at r is equal to 0. So using this Taylor expansion, then I can plug that in, and I can get half, right, times rho of r times the first term is phi of r at 0. This is simply the potential at r is equal to 0. It's just a value, right? So I can pull this out of the integral. So the first integral would simply be phi 0 rho of r d cube r integral. Similarly, for the second term, this is also a constant because it's at one particular r. So for the second term, I would have rho of r, right, times ri, and this is just a constant. So I would have dou phi by dou ri at ri is equal to 0, right, and this is d cube r, right. So now if I look at this, this is the dipole moment that we defined as pi, right? And then I have this here, a derivative dou q by dou ri, right? And dou q by dou ri, dou phi by dou ri is essentially negative of the electric field, because the electric field is gradient dou phi by dou r, right? So here I have dou phi by dou ri, so I have electric field value at r is equal to 0 and a negative sign with it because of the gradient here. So I have negative electric field times EI times PI, right? And this is EI at r is equal to 0. Or I can just write this as P dot E. Similarly, you could do the thing with quadrupole movement, like how we have done before for potential, and you can see what that term would be. So the multipole expansion is very useful in that sense. So now if you want to look at, for example, how two dipoles interact, the multipole expansion makes it so easy. So let's say I have a dipole, pointing in this direction, the first dipole, right? And now I bring in another dipole here, pointing in some other direction, P2. So I have P1 and P2, and this is R, the distance between these dipoles, right? And I would like to find out the energy of this interaction between these two dipoles. This is the most common type of interaction you would see in most of the solids. Anytime a dye is excited, a color is excited, you see these dipole-dipole interactions so often. These are ubiquitous. So, let's try to see what is the energy of this dipole-dipole interaction based on the multipole moments that we just discussed. So we know how the potential from a dipole should look like. It should just look like the dipole term, and the dipole term is essentially equal to Ri by r cube integral rho of r prime d cube r prime and another r prime here, right? So we call this pi, right? And then we had pi ri by r cube. So we later saw that this is nothing but p dot r by r cube. This is the first term in the potential that survives because the charges within this dipole are so close compared to r that the first term, the monopole term, total charge is 0. Right? So the first dominant term is the dipole term, which we know for the potential at r is p dot r by r cube, and of course you have a k here in the front, which was outside the integral. So k p dot r by r cube. So now I have this second um, dipole moment P2. So this dipole moment P2 at a distance r is going to experience an electric field, right? And that electric field is given by negative gradient of the potential, which is k times p dot r by r cube. And k is constant, so I can pull that out and I can just have p dot r by r cube, right? So if you do the derivative here, so for r cube you would get a minus 3, right? And p dot r by r to the power 5 r to the power 5 with an r vector here. I'll leave the differentiation to you. You can figure that out. And if you do with this, you would essentially get 1 over r cube p dot r, just p, sorry, right? Or plus, you get plus. So this extra minus sign makes this positive and this negative, right? So the electric field experienced at r by the dipole P2 is essentially k times um, uh, 3 p dot r by r to the power 5 r minus p by r cube. So now we have the electric field and we have the dipole moment. And from our previous discussion of looking at the energy, we saw from the dipole expansion of this rho of r phi of r d cube r that for the dipole term, the energy was simply P dot E. So here I have at R2, I have the dipole moment is P2 dot the electric field is this, right? So I have K times P2 dot 3 P dot R by R to the power 5 R minus P by R cube, P1 by R cube, and this is P1 because the electric field is coming from P1, right? So then you can just expand this and then get the total work done or the total energy as E times P2, which gives you K times P1 dot P2 by R cube minus 3 P1 dot R P2 dot R divided by R to the power 5. So the multipole expansion makes it very, very easy to look at things like the interaction of dipoles. And even quadrupole effect is very easy to see in this. You can also look at the work done by a quadrupole, just like how we derived for the dipole moments, but I'm not going to get into that. But what I want you to realize is by using a simple mathematical trick of Taylor expanding a function like 1 over r minus r prime, we were able to segregate terms into monopole, dipole, quadrupole, so on and so forth. So depending upon the geometry, depending upon the structure of the charge distribution we have at the origin, for example, if we have a dipole, we know that from very far from the origin, the monopole term is going to be cancelled. So we can pick out terms that would be dominant directly and further simplify the problem. And this leads us to realize something like the interaction energy of two dipoles. Imagine working out, if I had one plus charge, one minus charge here, and one minus charge, one plus charge here. Imagine using Coulomb's law to figure out the energy of this system. It would become very, very difficult. So instead of that, by simply Taylor expanding, we have cleared out certain terms, and we can directly arrive at what is the interaction energy in a very simplified fashion. So that is the use of multipole expansion.